There is a fact about the equations that govern reality that you were never told in school. Not because it is controversial, not because it is new, but because the implication is so uncomfortable that the people who teach physics would rather skip past it than explain what it actually means. Every fundamental equation in physics works the same forward and backward in time. Newton's laws, Maxwell's equations, the Schrödinger equation, Einstein's field equations. You can run them in reverse, and they produce equally valid physics. There is nothing in the mathematics of reality, nothing in the deepest description we have of how the universe operates, that says the past causes the future, but not the other way around. The arrow of time, the thing you experience every second of your life, the assumption that cause comes before effect, that what happened yesterday produced today and today will produce tomorrow, that arrow does not appear anywhere in fundamental physics. It is not there. It was never there. And the people who understand this best, the people who work with these equations professionally, have known this for over a century. That should bother you. Because if the laws of physics genuinely do not distinguish between past and future, then something we all take for granted, something we build our entire understanding of choice and consequence and identity on, is not a feature of reality. It is a feature of us. A bias, a habit of perspective. And a small but growing group of physicists has been asking for decades, what happens if you take that symmetry seriously? What happens if you let causation run in both directions? What happens if you accept that the future can influence the past? The answer is retrocausality, and it is not fringe, it is not speculation, it is a position supported by published theorems in the Proceedings of the Royal Society, by experimental results confirmed to 11.5 standard deviations, and by a research community spanning Chapman University, Tel Aviv University, Cambridge, and San Jose State. It has its own entry in the Stanford Encyclopedia of Philosophy, first published in 2019, and substantially revised as recently as November 2003. And the reason you have almost certainly never heard of it is not that it was disproven. It is that the implication, followed all the way to its conclusion, is something that most physicists would rather not say out loud. Because if retrocausality is real, if the future genuinely shapes the past, then the present you think you are living in right now, the moment you believe is open, the decision you think you are about to make, was already constrained by outcomes that have not happened yet. And that is not the unsettling part. The unsettling part is what it means about whether the present was ever yours to begin with. But we are getting ahead of ourselves. Let me tell you about the man who first cracked this open, and why it was personal for him in a way that nobody in physics talks about. John Archibald Wheeler was born on July 9th, 1911, in Jacksonville, Florida. He earned his doctorate at 21, studied under Niels Bohr in Copenhagen, and became one of the most important physicists of the 20th century. He coined the terms black hole, wormhole, and quantum foam. He supervised more than 50 doctoral students, including Richard Feynman, Kip Thorne, Hugh Everett, and Jacob Bekenstein. In January 1939, he greeted Bohr at the Princeton docks when Bohr arrived carrying the secret news of nuclear fission, and together they wrote the paper explaining the mechanism that would make the atomic bomb possible. But the thing that defined Wheeler's life, the wound that shaped his physics, happened in 1944. Wheeler had a younger brother named Joe. Joe Wheeler had a PhD in American history, a wife, a baby daughter. He was fighting in Italy during the Second World War. Wheeler was at the Hanford site in Washington State, working on the nuclear reactor that was feeding plutonium to Los Alamos for the bomb. And in late summer of 1944, Joe sent his brother a postcard, 2 words: hurry up. Joe knew what John was working on. He knew a weapon was coming that could end the war, and he was asking his brother, from a foxhole in Italy, to make it happen faster. On October the 25th, 1944, Joe Wheeler was killed near Florence in fighting against the Germans. John did not learn immediately. When the first nuclear explosion was detonated at Trinity in July 1945, John Wheeler's thought was not triumph. It was a single thought: I hope I am not too late. He was. The bomb came months after his brother died, and Wheeler carried that timing for the rest of his life. He wrote in his memoir, "One cannot escape the conclusion that an atomic bomb program started a year earlier and concluded a year sooner would have spared 15 million lives, my brother Joe's among them." His daughter said that as he got older, he wept often over this brother. Think about that for a moment. A man haunted by time, a man who spent the rest of his career unable to stop thinking about whether it was possible, even in principle, to reach backward and change what had already happened. In 1978, Wheeler proposed something that would become one of the most disturbing thought experiments in the history of physics. He called it the delayed choice experiment. Here is how it works. You send a single photon into a device called a Mach-Zehnder interferometer. The photon hits a beam splitter and, according to quantum mechanics, takes both paths simultaneously. At the end of the two paths, you can choose to insert or remove a second beam splitter. If you insert it, the two paths interfere, and you see wave-like behavior. If you remove it, you detect which path the photon took, and you see particle-like behavior. Standard quantum mechanics so far. But here is Wheeler's twist. You make the choice after the photon has already entered the device, after it has already passed the first beam splitter, after, according to any reasonable understanding of time, it has already decided whether to behave like a wave or a particle. And when you actually run this experiment, the result is exactly what quantum mechanics predicts. If you insert the second beam splitter, you get interference. If you remove it, you get which path detection. Every time. The photon's behavior at the first beam splitter, in the past, appears to be determined by your choice at the second beam splitter, in the future. Wheeler made it cosmic. Imagine a photon from a distant quasar emitted billions of years ago that encounters a massive galaxy acting as a gravitational lens. The galaxy splits the photon's path, sending it around both sides. Billions of years later, on Earth, you choose whether to set up a telescope that shows which path the photon took, or a detector that shows interference between both paths. Your choice today in this room seems to reach back billions of years to determine what that photon did when it passed the galaxy. In 2007, a team at École Normale Supérieure de Cachan published the definitive laboratory implementation in Science. Single photons from a nitrogen vacancy center in Diamond, a quantum random number generator making the choice. The choice was space-like separated from the photon's entry, meaning not even light could have carried the information in time. The closed configuration showed 94% interference visibility. The open configuration showed which path determination, with an error probability of less than 1%. Exactly as Wheeler predicted, exactly as quantum mechanics demanded. The photon's past was contingent on the experimenter's future choice. Wheeler himself did not call this retrocausality. He was careful. He said, "No elementary quantum phenomenon is a phenomenon until it is a registered phenomenon brought to a close by an irreversible act of amplification." He framed it as participatory, not causal. But the data was sitting there. The implication was sitting there. And the question it opened, the question of whether the future genuinely constrains the past, was not going to close just because the man who asked it was too cautious to follow it all the way. Because Wheeler's experiment, as unsettling as it is, does not by itself prove that the future causes the past. It proves that quantum mechanics is weird in a specific way, that the photon does not have definite properties until measurement. But there are interpretations that explain this without backward causation. The Copenhagen interpretation says the question of what the photon did before measurement is meaningless. Many worlds says it took both paths in parallel realities. Neither requires time to run backward. To understand why retrocausality is not just one interpretation among many, why a growing number of physicists believe the future really does shape the past, you need to understand a theorem, the most important theorem in the history of physics. A theorem that was ignored for years, that was considered a curiosity, that was dismissed as unprofessional, and whose author died before the world acknowledged what he had done. That theorem belongs to a man from Belfast who could not afford grammar school. John Stuart Bell was born on July 28, 1928, into a working-class family in Belfast, Northern Ireland. His mother Annie told her children that with education they could wear their Sunday suits all week. Of her 4 children, only John was able to stay in school past the age of 14. And even then he attended Belfast Technical High School instead of the grammar schools because his family could not afford the fees. At Queen's University Belfast, Bell wanted to study physics but could not afford to begin immediately. He spent a year working as a technician in the physics department, earning money to pay tuition before he could start his degree. Think about that. One of the most important physicists in history started by sweeping labs and maintaining equipment because the class system of post-war Belfast nearly locked him out of science entirely. Bell eventually earned his PhD and took a permanent position at CERN in the theoretical division, where his primary job was accelerator physics, particle beams, magnet design, practical work. His research into the foundations of quantum mechanics, the work that would change everything, was done in his spare time, on sabbaticals, on weekends, in the margins of a career that the physics establishment considered his real job. What drove Bell was a question that had been eating at him since he was an undergraduate. In 1952, the physicist David Bohm had published 2 papers proposing a hidden variables interpretation of quantum mechanics. Bohm's theory reproduced all the predictions of standard quantum mechanics, but did so using particles with definite positions guided by a pilot wave. It was a fully deterministic theory. It was mathematically consistent, and it directly contradicted a proof by John von Neumann that supposedly demonstrated hidden variables were impossible. Bell read Bohm's papers and was furious. Not at Bohm, at the entire physics establishment that had failed to tell him Bohm's theory existed. He later wrote, "Why then had Born not told me of this pilot wave, if only to point out what was wrong with it?" And when he went back and examined von Neumann's impossibility proof, the one that was supposed to settle the matter, Bell found a flaw. He called the proof not merely false but foolish. For 12 years, Bell turned this over in his mind. And then, during a sabbatical in 1963 at the Stanford Linear Accelerator Center and Brandeis University, he produced the result. Published in 1964 in a small journal called Physics, Volume 1, Issue 3, pages 195 through 200, a 6-page paper, the most important 6 pages in the history of physics. Bell's theorem proves that no theory satisfying 2 assumptions can reproduce the predictions of quantum mechanics. Those assumptions are locality and realism. Locality means that an action performed here cannot instantaneously affect something over there. Realism means that physical properties exist before you measure them. Together, they produce a mathematical inequality, Bell's inequality, that limits how correlated 2 distant measurements can be. Quantum mechanics violates that limit. It predicts correlations stronger than any locally real theory can produce, and if Bell's theorem is correct, then one of those 2 assumptions, locality or realism, must be wrong. The universe is either non-local, meaning distant events influence each other instantaneously, or it is not real in the classical sense, meaning properties do not exist until measured, or both. This is not an interpretation. This is a mathematical proof with experimental consequences. and testing it became the obsession of a young French physicist who was warned to his face that the attempt would end his career. Alain Aspect was born on June 15, 1947. In 1974, returning from a teaching stint in Cameroon that he had taken in lieu of military service, Aspect read Bell's papers. He later described the experience the way his friend Nicholas Gessin described it, as love at first sight. After 1 hour, he said he knew he wanted to work on that subject. Aspect traveled to CERN to consult Bell directly. Bell listened carefully. Then he asked a question that tells you everything about how the physics establishment viewed foundational research. Bell asked, "Do you have a permanent position?" Bell explained, "You know, doing this kind of subject, people are going to think that you are a crackpot." Aspect did not know the English word crackpot and asked Bell to explain it. Bell said, "Most people think that the subject is not interesting, that one has to be crazy to embark into that." Aspect told Bell he had a permanent position and could not be fired. Bell said, "Okay, let us do science." Between 1981 and 1982, Aspect and his team at the Institut d'Optique in Orsay, France, ran 3 increasingly definitive experiments. The source was a calcium atomic cascade producing pairs of entangled photons. The first experiment, published August 17, 1981, violated Bell's inequality by more than 9 standard deviations. The second experiment used 2-channel polarizers and the CHSH inequality, and the third, published December 20th, 1982, was the one that mattered. Aspect used acousto-optical switches operating near 50 MHz to change the measurement settings, while the photons were still in flight. The photons had about 40 nanoseconds of transit time across the 12-meter separation, and the switches flipped faster than light could travel between the detectors. This partially closed the locality loophole, the possibility that one detector could signal the other. Bell's inequality was violated by 5 standard deviations. The universe was not locally real. That was confirmed. What it meant was a different question entirely. But before we go deeper into what it means, there is a misconception that needs to be corrected. Because if you have spent any time watching quantum physics content on YouTube, you have almost certainly encountered a video claiming that the delayed choice quantum eraser experiment proves retrocausality, proves that the future can change the past, proves that information travels backward in time. Those videos are wrong, and understanding why they are wrong is essential to understanding why the real case for retrocausality is so much more disturbing than the pop science version. The delayed choice quantum eraser experiment was published in January 2000 in Physical Review Letters by Yoon-Ho Kim, Marlon Scully, and collaborators at the University of Maryland, Baltimore County. The setup uses a 351.1 nanometer argon laser to generate photon pairs through spontaneous parametric down conversion in a beta barium borate crystal. One photon, the signal, goes to a detector called D0. The other, the idler, is routed through beam splitters to one of 4 detectors. Detectors D3 and D4 preserve which path information. Detectors D1 and D2 erase it. And here is the part that gets people excited. The signal photon is detected 8 nanoseconds before the idler photon reaches its detector. The choice to erase or preserve path information happens after the signal photon has already been recorded. When you look at the coincidence data, you find that D0 detections correlated with D1 show an interference pattern. D0 correlated with D2 shows interference with a phase shift. D0 correlated with D3 or D4 shows no interference. It looks like the later choice of whether to erase path information retroactively determines whether the earlier signal photon produced interference. But there is a fact that the pop science videos almost never mention. If you look at the total pattern at D0, all detections combined without sorting by which idler detector fired, there is no interference pattern. None. The fringes from D1 and D2 are complementary. They are exactly out of phase. When you add them together, they cancel perfectly, producing the same featureless, single-slit envelope as the witch path detectors. The interference pattern only appears when you sort the data after the fact. When you use the idler detection results to select subsets of the signal data, this is post-selection, not retrocausation. As Sabine Hossenfelder put it, I could throw coins on the floor and then later decide to disregard some of those and create any kind of pattern. Clearly, this does not rewrite the past. Sean Carroll made the same point. From an Everettian perspective, the result makes perfect sense without anything traveling backward in time. And in 2204, Weijer and van Neerven published a mathematical proof in quantum studies. Mathematics and foundations showing that both Wheeler's delayed choice experiment and the quantum eraser produce exactly the same final quantum state, regardless of time ordering. The quantum eraser does not prove retrocausality. It proves that entanglement creates correlations that can be revealed by post-selection. That is interesting, but it is not time running backward. So why does this matter? Because the real case for retrocausality is not built on misunderstood experiments or sensational YouTube videos. It is built on something much more rigorous and much harder to dismiss. It is built on what happened when physicists closed every remaining loophole in Bell's theorem and found themselves staring at an assumption they had never questioned. But closing those loopholes took decades, and the results were so definitive, so statistically overwhelming, that they did not settle the question. They sharpened it into something with teeth. In 2015, 3 independent teams ran what the physics community had been waiting for since Aspect's experiments: loophole-free Bell tests. Experiments that simultaneously closed both the detection loophole and the locality loophole, leaving no classical escape route. The first was at Delft University of Technology in the Netherlands. Ronald Hansen's team at Quitech used nitrogen vacancy centers in diamond, electron spins separated by 1.3 kilometers, with entanglement swapping to create the correlations. It was a heroic experiment. 245 successful trials over 220 hours of data collection. The CHSH parameter came out at S equals 2.42 plus or minus 0.20. The classical limit is 2. The p-value was 0.039. Modest statistical significance, but the first time both loopholes were closed in a single experiment. The second was in Vienna. Anton Zeilinger's team at the Institute for Quantum Optics and Quantum Information used polarization-entangled photons with superconducting transition edge sensor detectors. Their result was not modest. The p-value was less than 3.74 times 10 to the negative 31 power. That corresponds to 11.5 standard deviations. To put that in perspective, the discovery of the Higgs boson at CERN was announced at 5 sigma. Zeilinger's Bell test was more than twice that. It is among the strongest statistical results ever recorded in the history of experimental physics. The third was at NIST in Boulder, Colorado, led by Lyndon Sharm, with collaborators from the University of Waterloo and the University of Illinois. Entangled photons, superconducting nanowire detectors, p-values as small as 5.9 times 10 to the negative 9, approximately 7 sigma. The universe is not locally real. 3 independent experiments, 3 different teams, 3 different continents, 3 different physical systems, all confirming the same result. The classical worldview, the one where objects have definite properties and distant events cannot influence each other faster than light, is wrong. That is not a debate. It is settled physics. The 2022 Nobel Prize in Physics was awarded to Aspect, John Clauser, and Zeilinger specifically for this experimental program. But there was one more loophole, one that these experiments did not close, and it is the one that matters for this story. It is called the freedom of choice loophole, or more precisely, the measurement independence assumption. Remember Bell's theorem. It proves that no locally real theory can reproduce quantum predictions, but the proof assumes that the measurement settings, the choices about how to orient the detectors, are statistically independent of the hidden variables describing the particles. In the mathematical notation, the probability of the hidden variable lambda, given the measurement setting alpha, equals the probability of lambda regardless of alpha. The settings and the particles are uncorrelated. If that assumption fails, if there is some correlation between the measurement settings and the hidden variables, then Bell's inequality cannot be derived. The theorem does not apply, and local realism might survive. In 2018, a team led by Dominik Rauch at the University of Vienna attempted to push this loophole as far back into the past as physically possible. The experiment was conducted on January 11, 2018, at the Observatorio del Roque de los Muchachos on La Palma in the Canary Islands. They used two telescopes, the William Herschel telescope with its 4.2-meter mirror and the Telescopio Nazionale Galileo at 3.58 meters, separated by about 1 kilometer. Instead of using random number generators on Earth to choose the measurement settings, they used something that had been decided long before Earth existed. They used the colors of photons arriving from distant quasars. One quasar at roughly 7.8 billion light-years away, the other at roughly 12.2 billion light-years. The wavelengths of photons emitted by these quasars billions of years ago were used in real time to set the detector orientations for an entanglement experiment happening on the ground. Bell's inequality was violated by 9.3 standard deviations. The p-value was less than 7.4 times 10 to the negative 20, and because the measurement settings were determined by events that happened billions of years in the past, any hidden variable theory that wanted to explain the results by correlating settings with particles would need that correlation to have been established at least 7.8 billion years ago. The experiment excluded 96% of the space-time volume of the past light cone as a source of the correlation. That leaves 4%, and pushing it further would require photons from closer and closer to the Big Bang itself. There is a hard limit. You cannot push the loophole back beyond the initial singularity. But 96% is enough to make the point. If you want to save local realism by attacking measurement independence, you need a conspiracy that was baked into the universe from nearly the beginning of time. And here is where the road forks, because there are exactly two ways to violate measurement independence. Two ways to explain why the settings and the particles might be correlated, and they are very different from each other. The first is called superdeterminism. It says the correlation exists because everything, including the experimenter's choice of settings, was determined by the initial conditions of the universe at the Big Bang. The particles and the settings are correlated because everything is correlated. Because there is no true randomness anywhere. Because every event, including every thought you have ever had, was fixed at the beginning of time. Your feeling that you are freely choosing which detector to activate is an illusion. You could not have chosen otherwise. You were never free. The second is retrocausality. It says the correlation exists because the measurement settings, chosen freely by the experimenter in the present, causally influence the hidden variables of the particles in the past. The information does not flow forward from the Big Bang. It flows backward from the future. The experimenter really does choose. But that choice reaches back in time and constrains what the particles were doing before the measurement happened. Both options violate measurement independence. Both explain the Bell correlations without non-locality, but they do so in opposite directions. Superdeterminism runs the causal arrow from the deep past to the present, Everything was predetermined. Nothing was ever up to you. Retrocausality runs the causal arrow from the future to the past. You genuinely choose, but your choice reshapes what already was. And here is what should disturb you. Not which one is right. That is still an open question. What should disturb you is what they have in common. Because both of them, followed to their full implications, terminate at the same destination. Whether the present is closed because the past locked it shut, or whether the present is closed because the future already reached back and constrained it, the result is the same. The open present, the moment you think you are living in right now, the space where you think choices are being made, might not exist. Not because someone disproved it, but because the two remaining ways of explaining the most confirmed experimental result in the history of physics both require it to be an illusion. And the people who saw this first, who followed this thread decades before the loophole-free tests, who understood where this was heading before anyone else, were punished for it, exiled, silenced, dismissed. Their stories are the most damning indictment of the 20th century physics establishment that you will ever hear. And understanding what happened to them is essential, because the idea of retrocausality did not emerge from mainstream physics in 2017. It was proposed in 1947, 70 years before the Leifer-Pusey theorem, 70 years before the loophole-free Bell tests, and the man who proposed it was forbidden from publishing by his own doctoral supervisor. His name was Olivier Costa de Beauregard. He was a French physicist who had been thinking about the implications of special relativity for quantum correlations. In 1947, while working under Louis de Broglie, Costa de Beauregard realized something that should have rewritten the foundations of physics. He proposed that the correlations between entangled particles could be explained by a zigzag causal path through space-time. The influence from a measurement on one particle travels backward in time to the common source of the entangled pair, then forward in time to the second particle. No faster than light signals needed. No violation of relativity. The influence follows time-like trajectories the entire way. It is local in the strictest possible sense. The only cost is that causation runs backward through one leg of the trip. De Broglie heard the proposal and refused to let Costa de Beauregard publish it. The idea was too radical. It would damage their reputations. De Broglie forbade it. Costa de Beauregard had to wait until Feynman's work on positrons, which used backward-in-time particle trajectories in quantum electrodynamics, gave some respectability to the concept of things moving backward through time. Only then was he able to publish, by which point the physics community had already hardened its consensus around the Copenhagen interpretation, which handled the measurement problem by declaring the question meaningless. The zigzag explanation was ignored, buried, forgotten for decades. And Costa de Beauregard was not even the most dramatic case, because the physicist whose work would eventually lead to the formal proof that retrocausality might be required, the man whose ideas would inspire Bell's theorem, which would inspire Aspect's experiments, which would lead to the 2022 Nobel Prize, was treated far worse. His name was David Bohm, and what happened to him is one of the great scandals in the history of science. David Bohm was born on December 20th, 1917, in Wilkes-Barre, Pennsylvania. He studied under Robert Oppenheimer at Berkeley, where he made significant contributions to plasma physics that are still used in fusion research today. At Princeton, he worked closely with Albert Einstein. Einstein called Bohm his spiritual son. The two men spent hours walking together through Princeton, debating quantum mechanics, both convinced that the Copenhagen interpretation was incomplete. In 1951, Bohm published a textbook called Quantum Theory. It was one of the clearest, most brilliant expositions of the Copenhagen interpretation ever written. Einstein read it and told Bohm it was the best presentation he had seen. And here is the irony that should haunt you. The very act of explaining the Copenhagen interpretation so clearly was what convinced Bohm it was wrong. Writing the textbook forced him to confront every assumption, every gap, every place where the interpretations substituted philosophical hand-waving for physical explanation. By the time he finished writing, he knew there had to be something deeper. In 1952, from exile, Bohm published 2 papers in Physical Review that proposed a hidden variables interpretation of quantum mechanics. Particles have definite positions at all times, guided by a pilot wave described by the Schrödinger equation. The theory reproduces every prediction of standard quantum mechanics. It is mathematically consistent, it is deterministic, and it directly contradicted von Neumann's 1932 proof that hidden variables were impossible, a proof that the physics establishment had treated as gospel for 2 decades. I said from exile because by the time Bohm published those papers, he was no longer in America. In 1949, the House Un-American Activities Committee subpoenaed him to testify about Communist Party activities at Berkeley. Bohm invoked the Fifth Amendment. He refused to testify against Oppenheimer. He was arrested, released on bail, and eventually acquitted. But Princeton did not care about the acquittal. The university refused to renew his contract. He was finished in America. Bohm fled to Brazil in October 1951. Less than 1 month after he arrived, the United States consulate confiscated his passport. Think about that. An American citizen, acquitted of all charges, had his passport seized by his own government, while abroad, effectively imprisoning him in a foreign country. When Bohm became a Brazilian citizen to survive, the State Department declared he had lost his American citizenship. He did not recover it until 1986, 35 years later. After a lawsuit in Brazil, Bohm suffered severe depression. He sought electroconvulsive therapy. Nazi sympathizers at the University of Sao Paulo threatened to scare him off the campus. Einstein wrote a personal letter to the governor of Sao Paulo on his behalf. And throughout all of this, the physics establishment's response to his hidden variables papers, the ones that resolved a foundational question that had been open for decades, was devastating. Heisenberg called it a superfluous ideological superstructure. Wolfgang Pauli called it an uncacheable check. Einstein, who had encouraged Bohm and inspired the work, called it too cheap because it still required non-locality. The man who had pushed Bohm to challenge orthodoxy rejected the result because it did not go far enough. Bohm's papers were not refuted. They were ignored. The physics community treated them as an embarrassment, a minor footnote, a curiosity produced by a man who had been exiled for political reasons and was clearly not doing serious work. For years, students were not taught that hidden variables theories existed. Bell's fury about never having been told about the pilot wave was not unique. An entire generation of physicists was kept in the dark about a mathematically valid alternative to Copenhagen, not because it was wrong, but because the establishment found it philosophically inconvenient. And yet, Bohm's 1952 papers are the reason Bell's theorem exists. Bell read them and was inspired to ask a single question. Is there a way to experimentally distinguish between hidden variables theories and standard quantum mechanics? The answer was his theorem, and Bell's theorem is the reason Aspect ran his experiments. And Aspect's experiments are the reason the 2022 Nobel Prize was awarded. The chain goes like this. Bohm's papers led to Bell's theorem, which led to Aspect's experiments, which led to the loophole-free tests, which led to the most confirmed experimental result in the history of physics. And the man who started the chain died in a London taxi on October 27, 1992, on his way home from Birkbeck College, where he had been finishing his final book. The Dalai Lama called Bohm his science guru. The physics establishment barely noticed he was gone. Historian Olival Freire Jr. wrote, "By this ruse of history, Bohm's hidden variable interpretation, so poorly received in the 1950s, produced a byproduct which has been the main scientific achievement behind the changed landscape of the research on the foundations of quantum mechanics. The byproduct being, of course, every experimental confirmation of Bell's theorem that followed, all of it tracing back to a man the establishment tried to erase. Bell himself did not fare much better. He spent his career at CERN, where his official work was on accelerator physics. His foundational research was a side project. The physics community treated quantum foundations the way a university treats the philosophy department: tolerated, underfunded, and not taken seriously. When Bell published his theorem in 1964, the paper appeared in a small journal that folded shortly afterward. It took years for the significance to be recognized, and when it was recognized, it was because experimentalists, not theorists, decided to test it. On October 1st, 1990, Bell died suddenly of a cerebral hemorrhage in Geneva. He was 62 years old. He was reportedly nominated for the Nobel Prize that year and did not know it. The prize that was eventually awarded for experimental work testing his theorem came in 2000-2002. The Nobel Committee credited Bell's theorem as the theoretical cornerstone. Belfast, following a local law that prohibits naming streets after people, named a road Bell's Theorem Crescent in 2015. CERN named a road Route Bell at its Meyrin site, but Bell never saw any of it. At a 1988 lecture in Belfast, Bell spotted a man named Reggie Scott in the audience, someone he had worked alongside as a technician more than 40 years earlier. Bell left the assembled dignitaries, walked into the crowd, and spent time having a conversation about the old days. That is who he was. A man from a working-class background who never forgot where he came from, whose greatest contribution to human knowledge was done in his spare time, and who died before the world understood what he had given it. So the chain of outsiders is clear. Costa de Beauregard, silenced in 1947. Bohm, exiled in 1951, ignored for decades. Bell, working in the margins at CERN, dead before recognition. Aspect, warned he would be called a crackpot, waiting 40 years for Stockholm. Every major advance in our understanding of what Bell's theorem means for the nature of reality came from people the establishment tried to discourage. That pattern should tell you something about how physics handles ideas that are too uncomfortable to absorb. But the idea that the future shapes the past did not die with the people who were punished for it. It found new carriers, and two of them built frameworks that would take the vague intuition of backward causation and turn it into something precise enough to test. The first was John Cramer, a professor of physics at the University of Washington in Seattle. In 1980, Cramer proposed the transactional interpretation of quantum mechanics, elaborated in a landmark 1986 paper in the Reviews of Modern Physics. The interpretation is built on a startling foundation, the Wheeler-Feynman absorber theory of radiation, which uses both forward-in-time and backward-in-time solutions to Maxwell's equations. Here is how it works. When a quantum emitter produces a photon, it sends out a forward-traveling wave called the offer wave. This is the standard quantum wave function, psi, propagating into the future. When that wave reaches an absorber, the absorber generates a response, a backwards-traveling wave called the confirmation wave. This is the complex conjugate of the wave function, psi star, propagating into the past. The confirmation wave travels back to the emitter and arrives at the exact moment of emission. What happens next is the part that matters. The offer and confirmation waves enter a cycle, reinforcing each other until they satisfy all the quantum boundary conditions. At that point, a transaction is completed. The Born probability rule, the rule that tells you the probability of a quantum outcome, emerges naturally as the product of the offer wave and the confirmation wave, psi times psi star. Wave function collapse is not a mysterious interruption of unitary evolution. It is the completion of a handshake across time. The transaction is atemporal. It does not happen in time. It happens across time. The entire exchange, the offer, the confirmation, the completion occurs along the full extent of the transaction, simultaneously. The photon does not first travel from emitter to absorber and then somehow send a signal back. The forward and backward waves exist as a standing wave in space-time. The event is a single four-dimensional structure, not a sequence of steps. Kramer used an analogy that cuts through the abstraction. He said the transaction is like a debit card purchase. When you buy groceries, there is a nearly instantaneous electronic transaction between the cash register and the bank. The transaction enforces a law of conservation of money, but the transaction does not determine what you buy. It only confirms that you can afford what you have bought. Quantum transactions enforce the laws of physics, but they do not determine outcomes. They are the mechanism by which the universe confirms that an event is physically permitted. The physics community received the transactional interpretation with polite indifference. It was not attacked. It was not refuted. It was simply not engaged with. Kramer, who is also a science fiction novelist and has written more than 180 popular science columns for Analog Science Fiction magazine, noted with characteristic humor that his interpretation unfortunately pulls the rug from under a number of excellent science fiction works based on the weirder aspects of quantum mechanics. But there is nothing funny about what the transactional interpretation implies. If the universe really does conduct handshakes across time, if the confirmation wave genuinely propagates backward from the future to the past, then every quantum event is shaped by both its beginning and its end. The future is not determined by the past. The future and the past determine each other. And the present, the moment of the transaction, is not a point where the future is decided. It is a point where the negotiation between past and future has already been completed. The second framework came from Yakir Aharonov, born August 28, 1932 in Haifa. Aharonov's connection to this story begins with Bohm himself. As a student at the Technion in Israel, Aharonov wanted to write a thesis on a particular topic, but was blocked by his advisor Nathan Rosen. A colleague suggested he talk to a new arrival at the Technion named Bohm. Aharonov knocked on Bohm's door. Bohm said, "Okay, this interests me too. I will talk to Rosen. I will convince him." When Bohm later developed a severe allergy to sunlight and had to leave Israel, Aharonov followed him to Bristol, where they produced one of the most cited papers in the history of physics, the Aharonov-Bohm effect, published in 1959, demonstrating that charged particles can be influenced by electromagnetic potentials even in regions where both electric and magnetic fields are zero. The paper has received nearly 10,000 citations, but Aharonov's deepest contribution to retrocausality came in 1964, the same year as Bell's theorem. Together with Peter Bergman and Joel Leibowitz, Aharonov published Time-Symmetry in the Quantum Process of Measurement in Physical Review. The paper introduced what is now called the two-state vector formalism, or TSVF. The idea is that a quantum system between two measurements is described not by a single state vector evolving forward in time, but by two state vectors, one evolving forward from the past preparation, the other evolving backward from the future measurement. Together, these two vectors provide maximal information about the system. The implications are staggering. In standard quantum mechanics, the state of a particle is determined entirely by what happened to it in the past. In the two-state vector formalism, the state of a particle is determined jointly by what happened to it in the past and what will happen to it in the future. The future measurement is not just revealing a pre-existing state, it is actively participating in defining the state at intermediate times. In 1988, Aharonov, Albert, and Weidmann pushed this further with the discovery of weak values. A weak measurement is one so gentle it barely disturbs the quantum system. When you perform a weak measurement on a pre-selected and post-selected system, You get a weak value that can lie far outside the normal range of possible results. A spin 1/2 particle can yield a weak value of 100 for its spin component. That number is not a measurement error. It is a mathematical consequence of the two-state vector formalism, a signature of the backward evolving state interfering with the forward evolving state. The paper has been cited more than 2,200 times. Aharonov, now in his 90s at Chapman University, has said that his work was motivated by the suspicion that apparently random events in quantum mechanics are caused by events in the future. He has identified over 30 novel quantum effects across his career, and the framework he built, the two-state vector formalism, is one of the primary theoretical tools used by the current generation of retrocausal researchers. Now, before we go further, let me address something that might be building in the back of your mind. You might be thinking, okay, but this is all interpretation. The transactional interpretation. The two-state vector formalism. These are ways of talking about quantum mechanics, not new predictions. And you would be right. Every quantum experiment ever performed can be explained by standard forward-time quantum mechanics. The retrocausal interpretations reproduce the same predictions. So why should anyone take them seriously? And let me be clear about what retrocausality is not, because this is the second misconception that needs correcting. Retrocausality does not mean time travel. Nothing travels backward in time. No physical objects go from the future to the past. No macroscopic information is transmitted backward. The no signaling theorem is preserved. You cannot use retrocausality to send a message to your younger self, or to win the lottery, or to undo a mistake. The causal influence operates on hidden variables, on the unobservable ontic states of quantum systems, not on anything you can directly access or control. The retrocausal models are explicitly designed to be what physicists call retrocausal but not retro-signaling. The influence flows backward in time at the quantum level, but the thermodynamic arrow of time, the one driven by entropy, the one you experience every day, remains intact. At the macroscopic scale, the forward arrow overwhelms any microscopic retrocausal effects. You cannot exploit it. You cannot feel it. You can only detect its signature in the statistical patterns of quantum experiments. And even then, only indirectly, by the way it resolves problems that no forward-time interpretation can resolve without invoking something equally strange. Which brings us back to the question, why take retrocausality seriously if it makes the same predictions? The answer is that it does not just make the same predictions, it dissolves problems. It resolves the tension between quantum mechanics and special relativity by eliminating faster-than-light influences. It explains Bell correlations through local time-like causal paths, not through instantaneous action at a distance. It potentially restores both locality and realism, the two pillars Einstein spent his life defending. And it does so at a cost that, once you examine it carefully, is not a cost at all, because it simply requires you to take seriously something that the equations have been telling you all along. That the laws of physics are time-symmetric. But interpretations are not enough. To move retrocausality from a philosophical position to a scientific one, someone needed to prove that it is not just a nice way of talking about quantum mechanics, but that it might be required by the structure of quantum theory itself. That proof came in 2017, and it changed everything. But to understand the proof, you need to understand the argument that preceded it. And that argument was made by a philosopher, not a physicist, which tells you something about how far outside the mainstream this idea had been pushed. Hugh Price was born on May 17, 1953 in Australia. His father came from a family he described as poor even by South Wales standards. Working on the railways from the age of 14, Price became one of the most important philosophers of physics in the world, holding the Bertrand Russell Professorship at Cambridge from 2011 to 2020, and co-founding the Center for the Study of Existential Risk alongside Martin Rees and Jan Tallinn. Price's argument about retrocausality begins with a simple observation that is so obvious it is embarrassing that physics overlooked it for so long. The fundamental laws of physics are time-symmetric. We keep saying this, physicists acknowledge it freely, but then they immediately act as if it is not true. They build interpretations of quantum mechanics that treat the forward direction of time as fundamentally different from the backward direction. They assume that causes precede effects. They assume that the past constrains the future, but not the reverse. And when you ask them why they make this assumption, given that the laws themselves do not support it, they point to the thermodynamic arrow of time. Entropy increases. Eggs break and do not unbreak. That is what makes time asymmetric. But Price pointed out that this is not an explanation, it is a description. The thermodynamic arrow of time arises from a very specific cosmological fact, the extraordinarily low entropy of the early universe, what physicists call the past hypothesis. If the early universe had started in a high entropy state, there would be no thermodynamic arrow. Entropy would not increase in any preferred direction. The arrow of time is a contingent feature of our universe's initial conditions, not a fundamental feature of the laws. And at the quantum level, where systems are small and entropy gradients are negligible, there is no reason to privilege the forward direction. The equations do not care. If you take time symmetry seriously at the quantum level, if you treat the fundamental laws as genuinely symmetric, rather than paying lip service to that symmetry, while secretly building in a preferred direction, then retrocausality becomes not just possible, but natural. Future measurement outcomes constrain past quantum states in exactly the same way past preparations constrain future quantum states. There is no asymmetry to forbid it. The only reason physicists assumed it was forbidden is that they imported a macroscopic intuition, an intuition generated by the thermodynamic arrow, into a domain where that arrow does not apply. In 2012, Price formalized this into what is now called the T-SAR argument. He showed that if you accept three assumptions, realism about quantum states, time symmetry of the fundamental laws, and the discreteness of quantum outcomes, then retrocausality follows as a logical consequence. The argument hinges on the discreteness. In classical physics, time-symmetric evolution does not require backward causation, because continuous classical states can evolve symmetrically without constraint from the future. But quantum discreteness, the fact that measurement outcomes come in specific discrete values rather than continuous ranges, closes off the classical escape route. With discreteness, you cannot have time symmetry without retrocausality. That was the philosophical argument. But philosophy does not convince physicists. What physicists needed was a theorem with formal rigor. And that is what Matthew Leifer and Matthew Pusey delivered. Leifer is a physicist at Chapman University in California. Pusey is at the University of York in England. In 2017, they published a paper in the Proceedings of the Royal Society A, Volume 473, number 2202. The title was dry, as technical papers tend to be. Is a time-symmetric interpretation of quantum theory possible without retrocausality? The result was anything but dry. Leifer and Pusey proved that Price's argument holds under conditions even weaker than Price had assumed. You do not need to assume full realism about the wave function, the way Price did. You only need a much weaker condition they called lambda mediation, which states that the hidden variable lambda screens off correlations between preparation and measurement. Under this condition, and assuming time symmetry, retrocausality is mathematically required. Let me say that again because the significance cannot be overstated. If you believe the fundamental laws of physics are time-symmetric, which every working physicist does, and if you believe in lambda mediation, which is an extremely mild and widely accepted condition, then retrocausality is not optional. It is a theorem, a mathematical consequence, published in one of the most prestigious physics journals in the world. This is the paper that the physics mainstream has largely not engaged with, not because it was refuted, not because a flaw was found, but because the implication is uncomfortable. As Leifer himself acknowledged, there is not, to my knowledge, a generally agreed upon interpretation of quantum theory that recovers the whole theory and exploits this idea. It is more of an idea for an interpretation at the moment. The onus, he said, is on the retrocausal community to flesh out the idea into a complete theory, but the logical structure is there, the proof is there, and the community is growing. Ken Wharton at San Jose State University has been building something even more radical. His approach abandons the entire framework of evolving quantum states forward in time and replaces it with what he calls Lagrangian models. In Newtonian mechanics, you specify the initial state and the laws, and you calculate what happens next. In Lagrangian mechanics, you specify both boundary conditions, the initial state and the final state, and the system takes the path between them that satisfies Hamilton's principle. The entire history between boundaries is determined simultaneously. There is no moment-by-moment evolution. The universe does not unfold, it is computed all at once. Wharton uses the analogy of a crossword puzzle. The answer to one across constrains the answer to one down, but one down also constrains one across. The constraints flow in both directions simultaneously. There is no privileged direction. In retrocausal quantum mechanics, the past preparation and the future measurement mutually constrain each other, like interlocking crossword clues. Neither one is primary, neither one causes the other in the traditional forward time sense. They co-determine the system's history. In 2011, Wharton, together with Price and DJ Miller, published a paper in the journal Symmetry introducing the concept of action duality. They showed that a single photon passing through two polarizers sequentially is mathematically dual to a pair of entangled photons at space-like separation. If you can give a local causal explanation for the single photon case, which is uncontroversial, then action duality demands you can give a local causal explanation for entanglement too. And the only way to do that is retrocausality. Then in 2023, Price and Wharton published Why Entanglement in a paper available through the Philosophy of Science archive, arguing that entanglement itself, the most distinctively quantum phenomenon, is best understood as a consequence of retrocausal boundary conditions. The correlations that Einstein called spooky action at a distance are not action at a distance at all. They are local correlations mediated by a zigzag causal path through space-time, exactly as Costa de Beauregard proposed in 1947. 76 years later, the idea that was suppressed has been given a formal mathematical backbone, and all of this connects to a picture of the universe that Einstein himself articulated, though he may not have followed the connection to its end: the block universe. Eternalism, the view that past, present, and future are all equally real, that space-time is a four-dimensional structure where all events coexist, and that the flow of time is a subjective experience generated by our position inside the block, not a fundamental feature of reality. Einstein wrote about this explicitly. After the death of his lifelong friend Michel Besso in March 1955, just weeks before Einstein's own death, Einstein wrote to Besso's family, "Now he has departed from this strange world a little ahead of me. That signifies nothing. For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion." You probably read that as a poetic expression of grief, a physicist consoling himself with the idea that his friend's life is somehow preserved in the fabric of space-time. But Einstein was not being poetic. He was being precise. Special relativity proves that simultaneity is relative. What is now for you is not now for someone moving at a different velocity. If the present moment is observer-dependent, then there is no universal now slicing across the universe. And if there is no universal now, then the distinction between past and future is not a feature of space-time itself. It is a feature of your particular trajectory through space-time. The block universe does not unfold, it exists. Everything that has happened and everything that will happen is already there, laid out in four-dimensional geometry. Robert Gerock, a mathematical physicist at the University of Chicago, put it bluntly. There is no dynamics within space-time itself. Nothing ever moves therein, nothing happens, nothing changes. The experience of time passing, the feeling that the present is special, that the future is open and the past is fixed, is generated from within the block by entities like us, whose information processing moves along a particular direction through the structure. And here is where retrocausality and the block universe reinforce each other in a way that nobody wants to talk about. If the block universe is real, if past and future are equally real slices of a four-dimensional structure, then there is no metaphysical reason to privilege forward causation. Future events are just as real as past events. They are just as capable of serving as boundary conditions. In the block universe, retrocausality is not weird. It is the natural expectation. What would be weird is if causation only ran in one direction through a structure that itself has no preferred direction. The Lagrangian picture, the Kramer handshake, the two-state vector formalism, the zigzag path through space-time, all of them describe the same fundamental idea from different mathematical angles. The universe is not a story being told from beginning to end. It is a completed structure, and the laws of physics are the constraints that hold the structure together. Past preparations and future measurements are both boundary conditions. The system between them is determined by both simultaneously. And the experience of an open present, the feeling that right now is the moment where decisions are being made and the future is not yet written, is not a feature of the physics. It is a feature of what it feels like to be a localized information processing system inside a structure that was completed before you were part of it. That last sentence is the third foreshadow, and I want you to hold it because we are about to follow the implication all the way to the end. The place where the physics arrives at a conclusion about you. Not about photons, not about hidden variables, not about Bell's inequality or measurement independence, or the Leifer-Pusey theorem. About you, about the experience you are having right now in this moment of time passing and choices being made. And it is worse than you think. Let me be precise about what has been established so far, because the next step in this chain is one that most discussions of retrocausality stop short of taking, and they stop short for a reason. Bell's theorem proves that no locally real theory can reproduce the predictions of quantum mechanics. The loophole-free tests confirm those predictions to 11.5 standard deviations. The cosmic Bell test pushed the freedom of choice loophole back 7.8 billion years, and the Leifer-Pusey theorem proved that any time-symmetric ontological model satisfying lambda mediation must be retrocausal. Every one of those results is published. Everyone is peer-reviewed. Everyone has survived scrutiny. The chain of inference is not speculative. It is not hand-waving. It is a sequence of mathematical proofs and experimental confirmations, each one locking the next one into place, each one published in journals that do not accept careless work. And the chain terminates at a question that the physics papers do not ask. Not because the question is unclear, but because the answer is too uncomfortable to write down in a professional publication. If the future causally influences the past, what does that mean for your experience of making choices in the present? The answer is not simple. It is not a bumper sticker. It requires you to hold two different versions of the same horror in your mind simultaneously. Because the two surviving explanations for the violation of measurement independence superdeterminate at the same conclusion about free will, but they arrive there by opposite routes, and the difference between those routes matters. It matters enormously, because one of them is a dead end, and the other is something much worse. Let me take them in order. Superdeterminism is the easier one to grasp, and the easier one to dismiss. It says that the correlation between measurement settings and hidden variables was established at the Big Bang. The initial conditions of the universe determined everything that would ever happen, including your thoughts, your choices, and the specific way you would orient a detector in a lab in 2015. The experimenter's free choice of measurement setting is not free. It was always going to be that specific setting, because the particles in your brain were always going to arrange themselves in the pattern that produced that specific neural firing, that produced that specific hand movement, that turned the dial to that specific angle. The correlation between your choice and the particle's hidden variable is not caused by any direct link between them. It is caused by the fact that both your brain and the particle descend from the same initial conditions at the Big Bang, and those initial conditions were precise enough to guarantee the correlation 14 billion years later. The problem with superdeterminism, and the reason the overwhelming majority of physicists reject it, is that it destroys science. Not metaphorically, not in some philosophical sense that only concerns epistemologists. Literally, if the universe can arrange correlations between detector settings and particle states without any causal link between the two, then there is no reason to trust any experimental result about anything. Every correlation you have ever observed in a laboratory could be an artifact of initial conditions rather than a genuine physical relationship. The aspirin you took correlates with your headache going away. But if superdeterminism is true, that correlation might not mean the aspirin caused the relief. It might mean that the Big Bang arranged for the people who take aspirin to be the same people who are going to have their headaches go away anyway. The correlation is real. The causation is an illusion produced by initial conditions so precise that they mimic causal structure without actually containing it. That sounds absurd, and it is. But that is what superdeterminism requires, and once you admit that possibility for quantum experiments, there is no principled way to exclude it from any experiment. Biology, chemistry, medicine, engineering, every empirical science rests on the assumption that observed correlations are evidence of causal relationships. Superdeterminism removes that assumption, not for quantum experiments specifically, but for all experiments everywhere. The Big Bang's initial conditions could be responsible for any correlation whatsoever. Anton Zeilinger, the man who ran the Vienna loophole-free Bell test and shared the 2022 Nobel Prize, put it plainly. We always implicitly assume the freedom of the experimentalist. This fundamental assumption is essential to doing science. If this were not true, then it would make no sense at all to ask nature questions in an experiment, since then nature could determine what our questions are, and that could bias our results. That is not a philosophical objection. That is an existential threat to the entire scientific enterprise. Consider what superdeterminism actually requires in practice. The 2018 cosmic Bell test used quasar photons from 7.8 and 12.2 billion years ago to set the detector angles. For superdeterminism to explain the observed Bell violation, the hidden variables of the entangled photons on the ground must have been correlated with the wavelengths of those quasar photons. That correlation would need to have been established at least 7.8 billion years ago, before the Earth existed, before the solar system formed, before most of the stars in the Milky Way had ignited. The initial conditions of the universe would need to have been fine-tuned to produce correlated wavelengths in two specific quasars, billions of light years apart. such that when their photons arrived at two telescopes on a mountaintop in the Canary Islands on January 11, 2018, they would produce detector settings that happened to correlate with the hidden variables of photon pairs generated by a laser on the ground between those telescopes. That is the scale of conspiracy superdeterminism requires. Not just for one experiment, but for every Bell test ever performed, on every continent, with every type of physical system, with every method of generating random settings. The initial conditions would need to be so precisely tuned that they could simultaneously account for experiments using radioactive decay, laser pulses, stellar photons, and quasar light to set their detectors, all producing the same statistical pattern of Bell violation across decades of experiments by independent teams who had no contact with each other. Bell himself was aware of this. In his later writings, he acknowledged that superdeterminism was a logical option, but said he would be very uncomfortable with a theory that required it. He compared it to the conspiracy theories of cranks. He wrote that it would mean the universe was engaging in a kind of grand deception, arranging everything to look as if local realism was violated, while actually preserving it through pre-established correlations stretching back to the origin of time. Gerard Hooft, the Nobel laureate who has been the most prominent defender of superdeterminism, has struggled for years to produce a fully worked model, and the models he has proposed have faced strong criticism from precisely this direction. If the initial conditions can fake Bell violations, what else are they faking? Where does the conspiracy stop? The answer, if you follow superdeterminism to its conclusion, is nowhere. The conspiracy is total. And a total conspiracy is indistinguishable from a universe where nothing can be known through experiment, which means superdeterminism, if true, makes itself uncheckable. It is the perfect irrefutable theory, and in science, a theory that cannot be refuted is not a theory. It is a philosophical position dressed in equations. So superdeterminism kills free will by killing everything. It says you never had a choice because nothing ever had a choice. The Big Bang determined all of it, from the orbits of galaxies to the firing of your neurons to the angle of a polarizer in a laboratory. That is conceptually clean. It is also, by near universal agreement among working physicists, a cure worse than the disease. Retrocausality is different. And the way it is different is what makes it so much harder to sit with. In retrocausal models, the experimenter genuinely chooses. That is the entire point. That is why retrocausality exists as a distinct option. The measurement independence assumption is violated not because the choice was predetermined from the Big Bang, but because the choice, freely made in the present, reaches back in time and constrains the hidden variables of the particle in the past. The correlation between settings and hidden variables is real, but the causal arrow points from the future to the past. Your choice is real. Your agency is real. The decision you make about how to orient the detector is genuinely yours. Nobody and nothing predetermined it. Price has been emphatic about this distinction, because it is the distinction that makes retrocausality scientifically viable, where superdeterminism is not. In retrocausal models, experiments still work. Correlations between observed variables still reflect genuine causal relationships. The scientific method remains intact. The only thing that changes is the direction of some of those causal relationships. Some of them run backward, but they are still causal. They are still reliable. They do not undermine the inference from correlation to cause the way superdeterminism does. And yet, think carefully about what it means for a freely made choice to retroactively constrain the state of a particle before the choice was made. The particle's hidden variable at the time it was emitted already reflects the measurement setting you will choose in the future. The past state of the system already encodes information about a decision that has not happened yet. Not because someone predicted your decision, not because your decision was determined by initial conditions, but because, in a retrocausal universe, the future is already exerting causal influence on the past. The hidden variable was shaped in part by an event that lies in its future. Let me make this concrete. In the cosmic bell test from 2018, the measurement settings were determined by quasar photons that had been traveling for 7.8 and 12.2 billion years. Those photons arrived at La Palma and their wavelengths set the detector angles. In a retrocausal model, the hidden variables of the entangled photon pairs produced on the ground were already correlated with those quasar photon wavelengths. Not because the Big Bang arranged the correlation, but because the quasar photon's arrival, billions of years in the future relative to the entangled pair's creation, reached backward and constrained the hidden variables at the moment of entanglement. The influence traveled backward along a perfectly local, time-like path. No faster than light signaling, no spooky action at a distance. Costa de Beauregard's zigzag from 1947. The influence goes from the measurement of one photon backward in time to the source, then forward in time to the measurement of the other photon. Every step of the journey respects Einstein's speed limit. The correlations that Bell proved cannot be explained by any locally real forward time theory, can be explained by a locally real retrocausal theory. Locality and realism both survive. The only casualty is the assumption that causes must precede their effects. And this is where you might feel a strange dissonance. Because on one hand, retrocausality seems to solve the problem more elegantly than any other interpretation. It restores the two things Einstein spent his life defending, locality and realism, at a cost that the equations themselves suggest is natural. On the other hand, the cost turns out to be everything you thought you knew about time. This does not violate the no-signaling theorem. You cannot exploit it to send information backward. The influence operates on hidden variables, the unobservable ontic states, not on anything you can measure directly or use to transmit a message. At the level of observable statistics, the forward arrow of time holds. Entropy increases. Eggs break. You cannot unscramble them by making a choice about a detector setting. The retrocausal influence is real but cryptic. It operates beneath the surface, shaping the correlations between quantum measurements without producing any macroscopically visible effect. But the fact that you cannot observe it does not mean it is not there. And the fact that it is there, if it is there, means something devastating for the experience you are having right now. Because if the future causally influences the past, then the past was never independent of the future. At no point, at no instant, at no moment in the history of the universe was the state of things free from the influence of what was going to happen later. The past was always being shaped by the future, at every scale where retrocausal effects operate, which in the quantum domain is everywhere. And if the past was never free from the future's influence, then the present, the boundary between past and future, the place where you think you are standing right now, is not a frontier. It is not the edge of an unwritten story. It is a joint, a hinge, a point where two directions of causal influence meet and produce a single self-consistent result. The present in a retrocausal universe is negotiated. That word matters. It is not a metaphor. In Wharton's Lagrangian models, the system between two boundary conditions takes the path that extremizes the action. The entire history between the initial and final conditions is determined simultaneously. As a single mathematical solution, the past boundary pushes forward, the future boundary pushes backward, and the trajectory between them, including the part you call now, is the unique path that satisfies both constraints at once. In Kramer's transactional interpretation, the same idea takes a different mathematical form, but arrives at the same place. The offer wave propagates forward. The confirmation wave propagates backward. They undergo cycles of reinforcement until the boundary conditions are satisfied and the transaction is completed. The event that you experience as Happening now is the completed transaction, the handshake across time. It did not happen in time. It happened across time. And when it completed, both the forward and backward waves collapsed into a single definite actual event that was consistent with everything before it and everything after it. Ruth Kastner, who extended the transactional interpretation into the relativistic domain in her 2013 Cambridge University Press monograph, argues that the transactions are the ontological primitive, not particles, not waves, not fields. Transactions, events that are constituted by the meeting of forward and backward influences. The things we call particles are just the observable residue of these transactions, and the things we call the flow of time are just the sequential experience of completed transactions by entities embedded within the network of transactions. This is a picture of reality in which nothing is primary except the mutual constraint between past and future. The present is not a moment that exists on its own. It is a solution to a pair of equations. One equation comes from the past, one comes from the future, and the solution, the unique answer that satisfies both, is the present you are experiencing. It is not determined solely by what came before. It is not determined solely by what comes after. It is the point at which forward causation from the past and backward causation from the future reach equilibrium. Both directions contribute. Both directions constrain. And the result, the specific state of affairs you experience as now, is the unique solution that satisfies both sets of constraints simultaneously. A negotiation between what was and what will be, completed before either side knew they were negotiating. And now ask the question, in this picture, what does it mean to make a choice? You believe you are choosing freely, and in a narrow technical sense, you are. Nobody predetermined your choice from the Big Bang. No initial condition forced your hand. The causal chain that superdeterminism requires, the one stretching unbroken from the first microsecond to the movement of your finger, does not exist in the retrocausal picture. You genuinely have the experience of weighing options, deliberating, deciding. That experience is real. Retrocausality does not deny it. But your choice was always going to be exactly what it is, not because it was predetermined from the past, the way superdeterminism would have it, but because the future, the outcome of your choice, the consequence that has not happened yet, was already reaching back and constraining the present in which the choice is made. Your choice and its outcome co-determine each other. They are not sequential. They are simultaneous. The choice produces the outcome, and the outcome constrains the choice. And both of these are happening at once, in a single self-consistent loop that was resolved before you were aware of being in it. This is not the failure of free will through determinism. This is something stranger and in some ways more unsettling. This is the failure of free will through self-consistency. Your choices are not forced by prior causes. They are forced by their own consequences. The future you are choosing is already shaping the present in which you choose it. And the present in which you choose it was already shaped by that future before you arrived in it. Think about what this means for regret. You look back at a decision you made. You wish you had chosen differently. The feeling is powerful, vivid, undeniable. You can almost see the alternate path, the one where you said yes instead of no, where you left instead of hesitated. In a forward deterministic universe, regret is poignant but simple. The past caused the future. You could not have done otherwise because the prior state of the universe made your choice inevitable. Regret is the brain's way of updating its decision-making for the future, a useful illusion. But in a retrocausal universe, regret takes on a different character. You could not have chosen differently, not because the past determined your choice, but because the consequences of your choice were already constraining the moment in which you made it. The alternate path you imagine, the one where you chose differently, is not just a path you failed to take. It is a path that is logically inconsistent with the four-dimensional structure in which it would have had to occur. The structure only admits one solution. Your regret is directed at a counterfactual that is not merely unlikely, but structurally impossible. It is like regretting that 2 + 2 does not equal 5. The feeling of regret is real. The object of the regret does not exist in any possible configuration of the block. And this is not limited to major decisions. Every micro-choice, every flicker of attention, every moment where your mind moves from one thought to the next is part of the self-consistent solution. The coffee you are drinking or not drinking, the position of your body, the specific neural firing pattern that is producing your conscious experience at this instant. All of it was always going to be exactly what it is. Not because someone or something forced it, but because the four-dimensional structure that contains it is self-consistent. And self-consistency means there was only ever one way it could be. There is an analogy that might help, though no analogy is perfect. Think of a novel, not one being written, but one that already exists as a complete object. A finished book sitting on a shelf. The characters in the book have experiences. They deliberate. They decide. From within the narrative, the characters appear to have agency. Their choices drive the plot. But from outside the book, there is no agency. Every word is fixed. Every decision was always going to be the decision it is. The character's feeling of making a choice is part of the text. It is real within the story. But it is not evidence that the story is being written in real time. The story was written. The book is complete, and the character's experience of an open present, of a future that could go either way, is simply what it is like to be a piece of text that cannot see the rest of the page. Now replace the book with the four-dimensional block universe. Replace the text with the physical states of particles and fields. Replace the characters with you. Hugh Price was asked directly about the implications. For free will, he gave an answer that is as honest as it is disorienting. He said, would it be the past controlling us, or us controlling the past? That is a subtle question, but one best left to philosophers. It is going to feel just the same. Either way, it is going to feel just the same. Sit with that for a moment. Because what Price is saying is that whether the present is genuinely open or retrocausally closed, the subjective experience is identical. You cannot tell the difference from the inside. The feeling of freedom, the sensation of deliberation, the conviction that the future is unwritten and you are the one writing it, all of that persists regardless of whether it is true. The experience of an open present is perfectly consistent with living inside a closed one. And if you cannot tell the difference from the inside, then the feeling of freedom is not evidence of freedom. It is just what being embedded in a self-consistent four-dimensional structure feels like from the perspective of an information processing system that can only access one time slice at a time. Your feeling of choice is not a window into the nature of reality. It is a consequence of your position within a structure whose true nature you cannot perceive from where you are standing. There is a deeper layer to this that gets overlooked in most discussions, and it has to do with what the block universe actually means for the experience of time itself. You are sitting or lying somewhere right now. You are listening to this, or reading this. You have the unshakable feeling that this moment is now, that the past is behind you and the future is ahead. That time is flowing from one to the other and that you are riding that flow. This feeling is so fundamental to your experience that you cannot imagine consciousness without it. The present moment feels special. It feels like the edge of reality, the place where potential becomes actual, where the unwritten future becomes the fixed past. But in the block universe, there is no edge, there is no flow. The entire four-dimensional structure exists, and every moment within it is equally real. The moment you call now is not privileged. The moment you remember as yesterday is just as present, in the ontological sense, as this one. The moment you anticipate as tomorrow is already there, not waiting to happen, not unwritten, not potential, already there, as real and as fixed as the moment you are experiencing right now. Your experience of time flowing is generated from within the block, by the specific way your brain processes information. Your brain receives sensory input in a particular order determined by the thermodynamic arrow of time, stores memories in a particular direction, and constructs a narrative of sequential experience. That narrative is what time flowing feels like. It is not a feature of the universe. It is a feature of you, a feature of being a particular kind of information processing system embedded in one direction of a four-dimensional structure. And the thermodynamic arrow that generates this experience is itself contingent. It arises, as Price argued, from the past hypothesis, the extraordinarily low entropy of the early universe. If the universe had started in thermal equilibrium, there would be no thermodynamic arrow, no entropy increase, no preferred direction for memory formation, no experience of time flowing. The arrow of time is a cosmic accident of initial conditions, not a fundamental law. And at the quantum level, where systems are small and entropy gradients are negligible, the arrow vanishes entirely. The Schrödinger equation runs equally well forward and backward. There is no direction for quantum evolution. The time symmetry that Price and Wharton and Leifer take seriously is not a philosophical preference they are imposing on the physics. It is the physics. The asymmetry is what was imposed by the specific initial conditions of our universe, and it is the asymmetry that needs explaining, not the symmetry. This distinction matters because it inverts the burden of proof. The default position in physics, the one supported by the mathematical structure of every fundamental law, is time symmetry. Retrocausality is what you get when you take the default seriously. Forward-only causation is the deviation. It is the thing that requires a special explanation, namely the thermodynamic arrow, the past hypothesis, the particular initial conditions of our universe. Strip away those initial conditions, and you are left with physics that does not know which way time flows. And at the quantum scale, where the thermodynamic arrow has negligible grip, you are left with a domain where the default, time-symmetric, potentially retrocausal behavior should reassert itself. That is exactly what the retrocausal program claims is happening. The quantum weirdness, the non-locality, the measurement problem, the apparent randomness, all of it is the residue of time-symmetric physics being forced through a time-asymmetric filter. The filter is your brain, your memory, your experience, the thermodynamic arrow that makes you perceive time as flowing in one direction. Strip away the filter and the weirdness resolves. The correlations are local. The randomness is deterministic. The measurement problem dissolves. The price is that you have to accept that the future is as real as the past and as causally potent. This is not speculation. It is the straightforward implication of special relativity. The relativity of simultaneity, confirmed experimentally to extraordinary precision, proves that there is no universal now that slices across the universe. What is simultaneous for one observer is sequential for another. If the present moment were a fundamental feature of reality, all observers would agree on which events are happening now. They do not. The present is observer-dependent, and an observer-dependent present is not a feature of the universe. It is a feature of the observer. Hermann Minkowski, Einstein's former mathematics professor, said it in a lecture in 1908 that Einstein initially resisted but eventually accepted completely. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. That union is space-time. the four-dimensional block, the structure in which past, present, and future coexist. Minkowski did not state this as a philosophical preference. He stated it as a consequence of the Lorentz transformations, and more than a century of experimental physics has confirmed it. Now here is what retrocausality adds to this picture that the block universe alone does not provide. Without retrocausality, the block universe is troubling but not devastating. The future is fixed, yes. But you could console yourself with the thought that at least the structure was assembled in one direction. The past caused the future. The arrow of causation, even if time does not flow, still points one way. The block was built from left to right, so to speak, even if the whole thing exists simultaneously once built. There is still an asymmetry. The past explains the future. The future does not explain the past. Causation, at least, respects the direction you feel it should. Retrocausality removes that consolation. In a retrocausal block universe, the structure was not assembled in any direction. It was not assembled at all. It exists as a self-consistent solution to a set of constraints that operate in both temporal directions simultaneously. The past shapes the future, and the future shapes the past, and the result is a structure that is consistent in both directions. There is no building direction. There is no direction in which the explanation flows. The structure is a crossword puzzle with constraints interlocking across both axes, completed in no particular order, consistent in every direction. And you are a word in that puzzle. Not a reader, not a writer, not a solver. A word, a piece of the structure that has the curious property of feeling like it is being written right now, in real time, even though the puzzle was completed before any of its pieces could know they were part of it. This is what it means, at the deepest level, for retrocausality to be real. It does not mean you can send a message to the past. It does not mean time travel is possible. It does not mean physics is broken or that the scientific method has failed. It means that the distinction between cause and effect, the most fundamental organizing principle of human experience, the thing you use to make sense of every event in your life, does not map onto the structure of reality at the deepest level we can probe. Causes and effects are categories that time-bound creatures like you impose on a structure that does not respect them. The structure is symmetric. The constraints run both ways. And the feeling that one thing leads to another, that the past produces the present, and the present produces the future, is the structure's way of being experienced from the inside by a system that can only see one slice at a time. There is a passage in the work of philosopher Jinan Ismail at Columbia University that captures this with unusual precision. She argues that the block universe does not eliminate agency. It reframes it. You are a deliberating system, a process that takes in information, evaluates options, and produces decisions. That process is real. It is part of the block. Your decisions are part of the structure. They are genuine in the sense that the structure would be different if you were not in it. The decisions matter. They are causally relevant, but they are not open in the sense that you feel them to be open. They were always going to be exactly what they are because the structure in which they occur was always self-consistent. Your deliberation is real. The outcome of your deliberation was always fixed. Both of those sentences are true simultaneously. The feeling of openness, the feeling that you could have chosen otherwise, is part of the deliberation process. It is not evidence that the process is undetermined. It is what determination feels like from the inside when the determined system is complex enough to model its own future states and compare alternatives before arriving at the state it was always going to arrive at. You are not an author writing a story. You are a character in a story that was never written sequentially. The story exists all at once, and the character's feeling of making choices, of being surprised by outcomes, of living in an open present where anything could happen, is part of what the character is. It is part of the structure. But it is not evidence that the present is open. It is evidence that the structure includes entities who experience it as open. And those are very different things. The philosopher of science Craig Callender at UC San Diego has written extensively about why the block universe feels so counterintuitive despite being the consensus view in fundamental physics. He argues that our time-passing experience is an evolutionary artifact, natural selection-shaped brains that model the world as a sequence of states, because that model is computationally efficient for creatures that need to predict near-future events and react to them quickly. The model works brilliantly for survival. But it is a model, and models do not need to be true to be useful. The model of a flat Earth is useful for navigating your neighborhood. It stops being useful at the scale of intercontinental travel. The model of a flowing open present is useful for making decisions. It stops being useful at the scale of fundamental physics. And here is the part that connects this back to retrocausality. If the flowing present model is just a model, if it is not a feature of reality but a feature of your cognitive architecture, then the model is not evidence about the nature of time. It is evidence about the nature of brains. And the physics, the actual physics, the equations and the theorems in the experimental results says something very different from what your brain tells you. The physics says time does not flow. The physics says the present is not special. And if the retrocausal program is correct, the physics says the future is as causally potent as the past. Your brain will reject this. It is built to reject it. The flowing present model is so deeply embedded in your cognitive architecture that abandoning it feels like abandoning sanity. But the entire history of physics has been the story of abandoning intuitive models when the evidence demands it. The Earth is not flat. The Sun does not orbit the Earth. Space and time are not separate. Matter is not solid. And the present, the thing you cling to as the realest thing in your experience, may not be what you think it is. Let me come back to the current state of this field, because I want you to understand that this is not ancient history. This is not a debate that happened in the 1980s and was quietly resolved. This is happening right now, and the trajectory is unmistakable. Price and Wharton wrote in The Conversation in March 2000 and 2003 that there is now a thriving group of scholars who work on quantum retrocausality. But, they noted, the program is still invisible to some experts in the wider field. It gets confused for a different view called superdeterminism. They described retrocausality as having the wind in its sails, and they listed the problems it dissolves: locality, realism, the measurement problem, the tension between quantum mechanics and relativity, as reasons why the wind is unlikely to die down. The active research nodes span multiple continents. At Chapman University in California, Matthew Leifer works alongside Mordecai Wagel and Kelvin McQueen, extending the formal framework that the Leifer-Pusey theorem established. At Tel Aviv University, Yakir Aharonov, now in his 90s, continues to push the two-state vector formalism into new territory alongside Lev Weidman and Michael Ridley. Aharonov has said in interviews that he was motivated from the beginning by the suspicion that apparently random events in quantum mechanics are caused by events in the future. When he and Bohm discovered the Aharonov-Bohm effect in 1959, it was considered a curiosity. It took years before the physics community accepted that a particle could be influenced by a potential in a region where no field exists. Now the effect is a cornerstone of modern physics, cited nearly 10,000 times. Aharonov has experienced this cycle repeatedly across his career. The idea is too radical. The idea is ignored. The idea turns out to be correct. Over 30 novel quantum effects bear his name, and the two-state vector formalism, his most radical proposal, the one that says every quantum system is shaped by both its past and its future, is the one that the current generation of retrocausal researchers treats as foundational. At San Jose State, Ken Wharton develops his Lagrangian models and publishes increasingly detailed accounts of how retrocausal boundary conditions can reproduce the full structure of quantum correlations. At the University of Sydney, Rod Sutherland has proposed a specific retrocausal extension of Bohmian mechanics. At the University of Western Ontario, Emily Adlam works on the philosophical and formal foundations of time-symmetric quantum theory. Ruth Kastner, associated with the University of Maryland, has published a Cambridge University Press monograph extending Cramer's transactional interpretation into the relativistic domain. 3 workshops on quantum retrocausality were organized under the auspices of the American Association for the Advancement of Science and the American Institute of Physics. In 2006, 2011, and 2016, organized by Daniel Sheehan at the University of San Diego, the proceedings were published in AIP conference proceedings. These are not fringe gatherings. The AAS is the world's largest general scientific society. The AIP is the professional body of American physics. When they host your workshop 3 times, the subject is no longer fringe. It is emerging. In 2025, Ridley published Many Retrocausal Worlds in the European Journal for Philosophy of Science, attempting a novel synthesis of Everettian branching with retrocausal boundary conditions. The title alone signals how far the field has come. A decade ago, the idea of combining many worlds with retrocausality would have been dismissed as incoherent. Now it is being explored in peer-reviewed philosophy of physics journals as a serious research program. And in August 2025, a researcher named Frank posted the paper to Arxiv proposing what he called the quantum time-symmetric interpretation, or QTSI. What makes this paper significant, regardless of whether the specific model survives peer review, is that it does something the retrocausal community has been waiting for since the Leifer-Pusey theorem. It proposes 3 specific experimentally testable predictions that could distinguish retrocausal models from standard forward-time quantum mechanics. The first prediction is a threshold-like disappearance of interference patterns above a critical system size, different from the gradual decoherence predicted by standard quantum mechanics. The second is anomalous photon decay rates in chaotic optical cavities, where the retrocausal boundary conditions would produce measurably different statistics than forward-time models. The third is novel interference fringes in time-symmetric diffraction setups that standard quantum mechanics does not predict. None of these experiments have been run yet, but the fact that specific predictions now exist is a qualitative shift. For decades, the objection to retrocausality was that it made the same predictions as standard quantum mechanics, that it was just interpretation, a different way of talking about the same mathematics without any empirical way to tell the two apart. If Frank's predictions hold up under theoretical scrutiny, and if experimentalists can design the necessary tests, retrocausality moves from philosophy to empirical science. It becomes testable, it becomes falsifiable, and the era of just interpretation may be ending. There are other experimental threads pulling in the same direction. In October 2023, David Arvidsson-Shuker and collaborators published a paper in Physical Review Letters showing that quantum simulations of closed time-like curves could be performed with a 25% success rate using entangled photons. The experiment did not create actual backward-in-time travel, but it demonstrated that quantum mechanics contains operational structures that behave mathematically as if information is being processed in non-standard causal orders. The line between as if and actually is exactly the line that the retrocausal program is probing. In 2000 and 2003, a team published results on the quantum Cheshire cat effect with neutrons in scientific reports. Using a silicon crystal interferometer, they spatially separated a neutron from its magnetic moment, its spin, and then used delayed choice techniques to probe the causal structure of the separation. A particle's property was found traveling along a different path than the particle itself. That sentence should not be possible. It is only coherent within a framework where the causal structure of quantum events is more flexible than forward time intuition allows. And throughout all of this, the mainstream physics community has been largely quiet, not hostile, not actively refuting. Quiet. The same quiet that greeted Costa de Beauregard in 1947, the same quiet that greeted Bohm's hidden variables papers in 1952. The same quiet that greeted Bell's theorem for a decade after its publication in 1964. Physics has a pattern when confronted with results it does not want to absorb. It does not argue. It does not engage. It simply looks the other way and hopes the result will go away on its own. The Copenhagen interpretation is a monument to this pattern. It was, from the beginning, a strategy of avoidance. Bohr's framework did not answer the question of what happens during a quantum measurement. It declared the question meaningless. It drew a line between the quantum world and the classical world and refused to specify where that line fell or what happened when you crossed it. Bell called this boundary the shifty split. In his final major paper, published in Physics World just months before his death in 1990, titled Against Measurement, Bell launched a precise, furious attack on the idea that measurement could be a fundamental concept in a physical theory, when nobody could define what constitutes a measurement and what does not. He asked whether a measurement requires a PhD, or whether a cat would suffice. He was not being clever. He was pointing at the absurdity that had been sitting at the center of quantum mechanics for 60 years, while the profession pretended it was not there. The Copenhagen interpretation is not a theory, it is a refusal to answer the question. And the physics establishment has been living inside that refusal for nearly 100 years, teaching it to students as though it were a solution, treating anyone who pushes past it as a troublemaker or a crank. Bohm was exiled. Bell was marginalized. Aspect was cautioned. Costa de Beauregard was silenced by his own supervisor. And the retrocausal researchers working today are operating at the periphery of a profession that would prefer not to hear what they have to say. Not because what they are saying is wrong, but because what they are saying, if followed to its conclusion, means that the thing you are experiencing right now, the open present, the flow of time, the feeling of free choice, is not a feature of reality. It is a feature of being trapped inside a structure whose architecture you cannot see. Think about the cost of that century of avoidance. 100 years of the smartest people on Earth declining to ask the most important question their own equations raised. 100 years of students being told that the measurement problem was solved by declaring it meaningless. 100 years of careers ruined, ideas suppressed, and research programs starved of funding because they asked questions the establishment found philosophically distasteful. If the retrocausal program is right, if the future genuinely constrains the past through local time-like causal paths, then the answer to the measurement problem, the answer to non-locality, the answer to the tension between quantum mechanics and general relativity, has been sitting in the structure of the equation since at least 1947, when Costa de Beauregard first saw it. 78 years, 3 generations of physicists trained to look away from the answer because the answer was too strange. That is not a failure of physics. That is a failure of nerve. And the people who paid the price for that failure, Bohm in exile, Bell in his spare time, Aspect warned about his career, Aharonov working for 60 years on ideas the mainstream refused to examine, those people deserved better from the profession they devoted their lives to. That should bother you. Not because retrocausality is certainly correct. It may not be. The field is still developing. The complete retrocausal theory that reproduces all of quantum mechanics in every domain, with every prediction accounted for, has not yet been constructed. Leifer himself acknowledged this honestly. There is not, to my knowledge, a generally agreed-upon interpretation of quantum theory that recovers the whole theory and exploits this idea. It is more of an idea for an interpretation at the moment. The onus, he said, is on the retrocausal community to flesh out the idea into a complete theory with distinguishing experimental predictions. But the formal arguments are rigorous. The experimental results that motivate them are among the most confirmed in the history of science. The logical structure is sound, and the reason this idea remains obscure, the reason you had almost certainly never heard of the Leifer-Pusey theorem before today, the reason the retrocausal interpretation does not appear in undergraduate quantum mechanics textbooks or popular science documentaries, is not that it failed some test, it is that it succeeded too well at following the implications of confirmed physics to a place the profession would rather not go. And now we arrive at the place where this has been heading since the first paragraph. Think about Wheeler's delayed choice experiment one final time. Not as a physics experiment, not as a demonstration of quantum weirdness, as a meditation on grief, a man whose younger brother was killed in Italy in 1944. A man who arrived at the Trinity test site hoping he was not too late, and who was. A man who spent the next 50 years of his career asking in increasingly sophisticated forms whether the present could reach back and reshape the past. A man who proposed an experiment in which a choice made now determines what a photon did at a beam splitter, and then that experiment was performed, and it worked exactly as he predicted. And the photon's past was contingent on the experimenter's future choice. There is a detail about the postcard that rarely gets mentioned. Joe Wheeler was a historian. He had earned his PhD in American history. He understood the weight of words on paper, the way a document can outlast its author, the way a message can reach through time to deliver its contents long after the sender is gone. Hurry Up was written by a man who understood exactly what he was doing. He was writing a message to the future. He was placing a demand on time itself, asking it to move faster, asking the causal chain to accelerate, asking his brother to make the bomb before the war killed him. And time did not comply. Or rather, in the retrocausal picture, the structure was already self-consistent. The postcard, the bomb, the war, the death were already locked together in mutual constraint. Joe's plea was part of the structure. It did not fail because it was unheard. It failed because the structure in which it existed was already complete, and the completeness included both the plea and its failure. Wheeler's great student Richard Feynman had his own encounter with the cruelty of time. In 1945, while working at Los Alamos, Feynman received a message that his wife Arlene had died of tuberculosis in Albuquerque. He had been visiting her every weekend, driving the 3 hours back and forth to sit at her bedside, and when the bomb was finally tested at Trinity, Feynman was the only person at the site who did not wear protective goggles. He watched the fireball with his naked eyes through the windshield of a truck because he had already lost the thing he was afraid of losing and did not see the point of protecting himself from anything else. Wheeler and Feynman had written papers together on the absorber theory of radiation, the very framework that uses both advanced and retarded waves. The framework that would later inspire Kramer's transactional interpretation. Teacher and student, both marked by loss, both working on physics that involved backward-in-time solutions, both producing frameworks in which the future participates in determining the present. The personal and the physical are not separate threads. They are the same thread, running in both directions. Wheeler drew a diagram he called the meaning circuit, a giant U with an eye at one end looking back at the other end. The universe begins. It evolves for billions of years. It produces observers. And those observers, through their measurements, participate in bringing the conditions of the universe into being. Past and future are not independent. They are coupled through the act of observation. The universe is a self-excited circuit. It brings itself into existence through the very act of being observed. This idea has a specific mathematical structure that is often overlooked in popular accounts. Wheeler was not suggesting that human consciousness creates reality in some mystical sense. He was suggesting that the quantum mechanical act of measurement, the irreversible amplification of a quantum event into a macroscopic record, is constitutive rather than revelatory. The measurement does not reveal a pre-existing state. It participates in determining what the state is. And because the measurement happens in what we call the present, while the quantum event it records may have occurred at any point in what we call the past, the participation is necessarily retrocausal. The present reaches back. The record-making event in the now constrains the quantum event in the then. Wheeler was explicit about the scale of this. He applied the delayed choice logic not just to laboratory photons, but to cosmological photons. Light from the early universe, gravitationally lensed by galaxy clusters, arriving at our telescopes today. Our choice of how to detect that light, whether to measure which path or interference, participates in defining the photon's behavior at the lensing event billions of years ago. We are participants in the history of the cosmos, not through some New Age fantasy, but through the straightforward application of quantum measurement theory to astronomical observation. This was not a metaphor offered at a retirement dinner. This was Wheeler's serious proposal for the architecture of reality, published in major journals and presented at conferences through the 1970s and 80s. And if you look at it clearly, it is a retrocausal proposal. The observer in the present participates in determining what happened in the past, but there is a wound underneath the framework. Wheeler did not arrive at these ideas in a philosophical vacuum. He arrived at them as a man who had spent 40 years wishing he could reach back in time and change one unbearable thing. A weapon that arrived too late. A brother who died in Italy 3 months before his first birthday as a father. A daughter, Mary Jo, who grew up without knowing her father and who married the quantum cosmologist James Hartle. The physics and the grief are woven together so tightly that you cannot separate them. Hurry up. Those were Joe's last words to his brother. 2 words on a postcard from a foxhole. And John Wheeler, for every remaining year of his life, kept returning to the same question, wearing different masks. Can the present change the past? Can an observation now determine what happened then? Can a choice made today reach backward and alter what was already fixed? The delayed choice experiment answers yes, in a limited quantum mechanical sense. Your choice of measurement determines what the photon did at the beam splitter. The photon's past is contingent on your future action. But it also answers no, in a sense that mattered to Wheeler, because in the block universe, the photon's behavior was never undetermined. It was always consistent with the choice you were always going to make. The past was not changed. The past was always what it was going to be, given the future that was always going to happen. In the block universe, there is no moment of adjustment. There are no moments at all. In the way you experience them, there is only the structure, complete, self-consistent, still. Wheeler could not save his brother, not because the physics forbids backward influence. The physics may well permit it. But because the physics that permits backward influence also requires that the past was always consistent with the future that actually occurs. In a retrocausal universe, Joe was always going to die on October 25th, 1944, not because that death was predetermined by conditions at the Big Bang, but because the entire 4-dimensional structure of reality, past and future, and every choice and every consequence taken together, already contained that event as part of its self-consistent solution. The future in which John Wheeler built the bomb too late was already constraining the past in which Joe sent the postcard. Hurry up was not a plea that could have been answered differently. It was part of the structure, a word in the crossword puzzle, interlocked with every other word, fixed by constraints running in both directions through time. not because fate demanded it, not because God wrote it, but because the whole structure is self-consistent, and self-consistency leaves no room for revision. This is retrocausality's cruelest implication. It does not say the past is fixed because you cannot change it. It says the past is fixed because the future, the one that actually happens, was always shaping it. Your feeling that the past could have been different is based on the assumption that the future was open. But if retrocausality is real, the future was never open either. Both directions were always locked together in mutual constraint. The past shaped the future, and the future shaped the past. And the result was a single, complete, negotiated structure in which nothing was ever up for grabs. Not because the universe is deterministic in the classical sense, not because some initial condition at the Big Bang controlled everything that would follow, but because the structure is self-consistent in both directions of time simultaneously. There is no room for anything to be different, because being different would violate the consistency constraint that holds the entire four-dimensional block together. Every event is the unique solution to a set of boundary conditions that include both its causes and its effects. And you, your thoughts, your choices, your experience of sitting here in this specific moment absorbing these specific words, are part of that solution. And that means the feeling you have right now, the feeling of processing new information, of having your understanding shift, of being unsettled by something you did not know before, that feeling is also part of the structure. Your surprise is not evidence of an open present. It is evidence that you are a piece of the structure encountering another piece of the structure for the first time from your limited perspective. The information was always there. Your encounter with it was always there. The fact that it feels new is just what self-consistent structure contains: entities whose information processing is sequential and whose memories point in only one direction. You cannot step outside the block to verify this. That is the final, most disorienting aspect of the whole picture. You are inside the structure. You have always been inside the structure. Every tool you have for investigating reality, every experiment, every observation, every thought, is a process occurring within the structure, and the structure is self-consistent. It will never present you with evidence that it is a block, because the block includes your inability to see it as a block. Your experience of an open present is part of the design, not designed by anyone, but part of the self-consistent solution that the structure represents. Wheeler spent his last years at Princeton, where he had started his career more than 7 decades earlier. He died on April 13, 2008, at the age of 96. He had received the Wolf Prize, the Enrico Fermi Award, the National Medal of Science, and the Einstein Prize. He had trained a generation of physicists who reshaped the landscape of modern physics. His daughter later wrote about a man who wept often in his final years over a brother he lost in 1944. And here is the thing that physics, for all its extraordinary precision, cannot resolve. Einstein wrote to the Besso family after Michel Besso's death in March of 1955, just weeks before Einstein's own death. For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. If that is true, if the block universe is real, then Joe Wheeler's death is not gone, it is not erased, it is not lost. It exists in the same four-dimensional structure, as permanently as John Wheeler's grief, and John Wheeler's physics and the photons in the delayed choice experiment, and the entangled particles in Aspect's calcium cascade, and the quasar light that traveled 12.2 billion years to set a detector angle on a mountaintop in the Canary Islands. And not just Joe Wheeler's death, everything, every event, Bohm's arrest and his acquittal and his passport being confiscated in Brazil, Bell's year as a technician at Queen's University, sweeping labs to earn tuition money, the moment Aspect read Bell's papers for the first time and fell in love with the subject. The moment Aharonov knocked on Bohm's door at the Technion, and Bohm said he would convince Rosen, Costa de Beauregard's supervisor telling him he could not publish. Bell's cerebral hemorrhage in Geneva in 1990. Bohm's heart attack in a London taxi in 1992. His final book unfinished on his desk at Birkbeck College. Every single one of these events is as real, in the ontological sense, as the moment you are occupying right now. They are not past. They are beside you in the four-dimensional structure, and if retrocausality is real, they are causally connected to you in both directions. Think about what that means for the chain of outsiders. Bohm's exile did not just cause Bell's theorem in the forward direction. In the retrocausal picture, the entire chain, from Bohm's papers, through Bell's theorem, through Aspect's experiments, through the loophole-free tests, through the Leifer-Pusey theorem, is a single self-consistent structure in which every link constrains every other link. In both directions, the discovery of the theorem shaped the exile that produced the papers that led to the theorem, not sequentially. Simultaneously, the structure exists as a completed whole. The narrative of cause and effect that I have been telling you for the past 2 hours, with one event leading to the next in a sequence, is a concession to the way your brain processes information. The reality, if the retrocausal program is correct, is that the events do not lead to each other. They coexist with each other. They constrain each other. And the story I am telling is not the way it happened. It is the way it looks from inside the block. That is either the most comforting thing physics has ever said, or the most terrifying. It depends on whether you see the block universe as a prison or a monument. Every moment preserved. Nothing lost. But nothing changeable either. The past is not behind you. It is beside you. It is beside you too. And perhaps at the quantum level, past and future are reaching toward each other in a handshake across time that was completed before either side knew it had begun. And here is what you will carry with you after this ends. You now know something about the equations that govern your reality that you did not know 2 hours ago. You know that the fundamental laws are time-symmetric. You know that a published theorem shows that taking that symmetry seriously leads by mathematical proof to retrocausality. You know that the experimental results supporting this chain of inference are among the most statistically significant ever recorded in the history of science. And you know that the physics establishment has spent nearly a century declining to follow these implications to their conclusion. You cannot unknow this. And the people who work on this, the Leifers and the Whartons and the Prices, the people who have spent their careers in the margins of a profession that would rather they do something more conventional, they cannot unknow it either. They go to sleep at night with these equations in their heads. They wake up in the morning and the equations are still there. And the equations say the same thing they said yesterday. The future constrains the past. The present is negotiated. The open moment you think you are living in might be a cross-section of a completed structure. That knowledge changes the texture of ordinary experience in ways that are difficult to articulate. You pour coffee, you look out a window, you make a decision about what to do next. And somewhere beneath the surface of those ordinary acts, if you have absorbed what we have discussed, there is a whisper, a question you cannot quite suppress. Was this moment always going to be exactly this moment? Was this choice always going to be exactly this choice? Is the feeling of openness, the feeling of possibility, the feeling that I could do something other than what I am about to do, just the structure's way of hiding itself from me? You will not be able to answer that question. Nobody can answer it from inside the block. But you will not be able to stop asking it either. And that inability to stop asking, that persistent discomfort, that sense that something about the present is not what it appears to be, is perhaps the most honest response to the physics. Because the physics does not resolve into comfort. It does not reassure. It sits there in the equations, in the experimental data, in the theorems, saying the same thing it has always said. The laws do not know which direction time runs. And neither, if you are honest about it, do you. The calculations have been checked. The Leifer-Pusey theorem stands. The experiments have been replicated on 3 continents, with 3 different physical systems. The time symmetry of the fundamental laws is not disputed by any working physicist, and the implication chain terminates here. Not at a mystery, not at something we do not yet understand, at something we understand too well to say comfortably. If retrocausality is real, then causation does not flow in one direction. Effects can precede their causes. The future is not determined by the past alone. The past is also determined by the future. Both directions are real, and both are operating at once, and the present is the place where they meet. But the implication nobody wants to follow to its conclusion is this: if the future is already influencing the present, then the present was never open. The choices you believe you are making right now were already constrained by outcomes that have not happened yet. Free will does not fail because the past determines the future. It fails because the future has already determined the past. And the version of reality you are experiencing right now is not unfolding. It was negotiated in both directions before you were part of it. You are not watching the story happen. The story already happened. You are the part of it that has to feel like it is happening now.